or run over time, you have enough time to leave. Welcome to this May's Masterclass by the Sydney Informatics Hub, and more specifically the Stats Consulting Group. I hope you can hear me well. If you can't, yeah, let me know in the chat. What do people say in the chat? Nothing. I guess that's a good sign. Cool. Well, yeah, let's get started. Today's talk will be structured into three kind of rough sections. The first section is going to be I'm going to talk about what SIH masterclasses are, and I'm going to talk about this talk. The second thing is I'm going to talk about sort of the history or the sort of background of linear regression or regression analysis that has led us to this place today. And lastly, I'm going to talk about sort of the more important topic of today, which is distributional regression. Okay, let's get started about SIH masterclasses. SIH masterclasses are standalone workshops on a particular topic. They run every third Thursday of the month, and you can find them on the upcoming workshop on the SIH website. There's a really cool calendar online where you can see what's coming up. So definitely check that out for future cool masterclasses. About this talk is heavily inspired by Gillian Heller's talk, who is here today, who gave a talk at the J.B. Douglas Awards of the Statistical Society of Australia in 2020. Her talk was titled "The New Normal: Distributional Regression," which I like for a lot of different reasons. I mean, as you guys remember, 2020 was a special year, and we were talking about new normals a lot. But there's also something about the normal distribution there and stuff. So I really like that title. I rewrote a lot of it for a new audience because that was an audience of statisticians, and today we have a lot of applied statisticians here. One thing I want to say as well is that at the end of this talk, we'll have a quick Q&A session. And if you would like, and this talk is also recorded, so if you don't really want your face to be seen on this recording, then I urge you to turn your cameras off if you're online. Okay, so let's talk about how we got here in the first place. And to really get started, I'd like to ask a little question to the audience. And I'd like to ask everyone how long a meter is. And I'm not talking about how many centimeters or how many kilometers a meter is, but what is the original definition of a meter? Does anyone have an idea? One step. Katrin says one step. Very good. Is there anything in the chat maybe? Nothing in the chat? Oh, well, one step is pretty good. And it gets pretty close to what it was. Here is a picture of one of the original meters. It was basically part of a building in France, and if you wanted to know how long something is, you just go to that building and figure out how long it is. It still exists to this day. And to go to the origins of the meter comes from the French Revolution, because in 1789, you guys know that the sort of royals were overthrown by the French Revolution, and a part of the French Revolution was the desire to replace features that were once part of the sort of royal regime. And one thing that people were specifically keen to replace was the toise, which is which was the main distance metric before the French Revolution. And the toise is defined as the distance between the fingertips of the outstretched arms of a man. And as you guys can probably imagine, that's a pretty variable metric, so not very reliable. And so what people came up with after the French Revolution was that the meter should be defined as 1/10,000,000th of the distance between the equator and the North Pole, which is also called a quadrant of the Earth. And the question is just how long is this distance of a quadrant? And a few people set off to figure out how long this distance was. One of them was Adrien Marie Legendre. And he was supposed to be, he was responsible for the quadrant surveyed within France. And he basically took a lot of measurements along sort of the French middle line. And you can see here, he took a lot of smaller sort of measurements. And then the question was, how do we combine those to figure out what sort of the distance is between this specific part next to Barcelona and the northern part of Dunkirk. And from this publication comes the so-called invention of the least squares method, which is to this day used to estimate a linear regression model. And what he basically did was he surveyed parts of this and then used this least squares method to combine all these measurements to a straight line through France. What's a bit spicy about the story is that Gauss, who's a, everybody kind of knows Gauss, he was a famous mathematician, went to Göttingen, where I went to as well. He later claimed that he had already been using these techniques since 1775. And that's a bit of a, that was a classic move by Gauss. At the time, anytime someone invented something, he would, pull out some of his drawers and take something out and basically claim that he'd already done this since ages ago. So it's not exactly 100% clear who was the first person to use it, but both of these people come pretty close. And that brings me back to linear regression analysis, which in its purest form is the relationship between a variable x and the variable y. And what we do in linear regression is we try to minimize the distance between this straight line going through our data cloud and the specific data points, which are outlined by arrows here. And this is also why it's called the least squares method, because we basically square the distance between the observations and the line, and the least amount of squares is where the line should go. Some of the assumptions that come with that is that we have one dependent variable y, and we have a few explanatory variables x, and the estimators of x are called beta. Those are the ones that are connecting the x to y. And part of this is also our error term, which is supposedly independent and distributed around 0 and has a constant variance. So in this case, our error term is normally distributed around 0 and has a constant variance sigma squared. This is also called the homoscedasticity of errors. If we go back to this graph, we can see that in this case, we can see the observations are neatly surrounding the line, and this is kind of an assumption we have with linear regression. But as any applied statistician will know, very, very often our errors are not normally distributed. This specific graph I made outlining sort of an error distribution. In this case, I have a dependent variable or target variable, which only is binary, so it can only be 0 or 1. And then I fitted a normal linear regression model to that. And we can see that our errors are basically bimodal, around minus 0.5 and plus 0.5. And this is a clear violation of our normality assumption. And even though the linear regression method has been going for a long time, only very recently people have started to investigate what could happen if we have a non-normal error distribution. Most importantly, Nelder and Wedderburn in 1972 came up with generalized linear models. Here are two pictures of them. And they were sort of the most prominent, this was sort of the most prominent publication following the violation of the error distribution or a generalization of linear regression. And at the time, this was a total game changer because before people didn't really know what to do in situations of abnormal errors. And what they have proposed basically is to relax the assumption of our error term into having basically a distribution that can be any exponential family. So let's go through the changes to a normal to linear regression quickly. We assume distribution y, and that has a it's called D, this distribution, and it has a exponential, it has an expected value mu, and it has a dispersion parameter p. And now what we can do instead of before, where we didn't have, where we basically just connected the mu to our explanatory variables, we now transform these explanatory variables using a link function h, and that allows us to basically stay within the range of the parameter that we try to estimate. This all sounds a bit abstract maybe, but if you remember a logistic regression model, for example, or if you remember a binary variable that can only be 0 and 1, what we're trying to figure out is how the probability changes that things could be 0 or 1. And this means that our probabilities can only be between 0 and 1. And this means that our link function ensures that even though our explanatory variables are, any normal distributions on the real line, we actually estimate only between 0 and 1 for a logistic regression model. But this could also be the gamma distribution, for example. The gamma distribution can only be positive, but it's not bound on the positive scale. And we have link functions in place that ensure that our parameters are properly estimated. The exponential family is a family of distributions which encompass most problems that we see in everyday life. Of course, part of the exponential family is the normal distribution. We also have the Poisson distribution, which we often use for count regression. Most prominently is the logistic regression model, often used in preliminary machine learning. But we also have the gamma, the inverse Gaussian, and the negative binomial distribution, for example. But what is really important about GLM is that we still assume a constant dispersion parameter phi, which means that we still assume that the variance of y doesn't really change over the range of explanatory variables. Here's a quick example of when we would use a generalized linear model. This is a quick mock example I pulled up. This is a probability of, as a student, of passing a certain exam on the y-axis, and then on the x-axis is amount of hours studied. And then each of these, black dots is basically one student. And then, supposedly with more studying comes the higher probability of passing. And we can estimate using the logistic regression model. In situations where we cannot assume a linear relationship between our dependent variable y and our explanatory variable x, we break this assumption, because we basically think in our model equations that we have still a linear relationship between x and y, even though it's changed to the link function. The linear predictor is still still assumes a linear relationship, and that's often not the case. This is a graph that is from a time when I was analyzing gym attendance for a popular gym in the small university town that I was studying at the time, where they basically wanted to figure out a model that would predict how many people were there at any given time, so that they could adequately plan their staff. And so this is a Friday, I think. This is a typical Friday in the gym, and you can see over the morning it's pretty stable, but then around the afternoon, evening, when people come back from work or studying, they want to work out, and then sort of around dinner time it drops off again. And this is a classic example of a nonlinear relationship between an explanatory variable and y. And in GLM we don't really have any good ways of implementing this into a model. And because of this reason, Hastie and Tibchirani, who was to this day still very prominent in the statistics and also machine learning community, they came up with this idea of the generalized additive model in 1986. And in this case, we again assume a distribution for y, which has an expected value mu and a dispersion parameter p. But in this case, we connect this expected value mu to our explanatory variables using what he calls smooth functions. And smooth functions basically could be anything that is a local smoothing of the explanatory variable. This could be like a local mean, or it could be polynomial splines. And these can be parametric or non-parametric. If we have smooth splines in its purest form, they're actually parametric. But if we have some kind of penalty term in there, which could be penalized splines, which were very prominent 20 years ago, then we have a non-parametric estimate. And but I think the smooth functions were probably the biggest reason why people were using them. But you can actually use these S terms for many different reasons. You can, for example, model spatial effects in there, which would induce like a local penalty around sort of geographical boundaries. You can have interaction terms, you can have random effects, and so on. But one thing that is still really relevant in even generalized additive models, even though it's so flexible, is that we still assume a constant dispersion term. And and this is what brought many people to come together to invent distributional regression. So let's talk about a distributional regression. And before I tell you what it is, I'd like to quickly come back to sort of intro stats. And I'd like to quickly ask everyone, what are the differences a distribution can have? And to give you some kind of ideas of what these differences could be, I put here a graph from a viable distribution, which can look vastly different depending on their parameters. But if we think about a distribution, how can it change? What kind of properties can we have in a distribution? Alex? Yeah, very good. That's the first one. We can have a location shift. A location shift looks like this. So we have a distribution, and then we basically increase the expected value or the median or whatever, and then we change location. That's good. Anyone have any other ones? Yeah, very good. Yeah, that's my next slide. Perfect. The next one is the scale. Thanks, Julian. Oh, yeah. Oh, it was you. Yeah, very good. Let's come to the shape in a second. Let's talk about the scale first. What is the scale difference? Scale difference means basically a variance difference or a dispersion difference. I mean, it's just the amount that it disperses around the mean or median value. And then Christy has said we have the shape, which is true. The shape encompasses many different things. I mean, you can have skewness, you can have kurtosis, but you can have many different ways in which a distribution can be different. You can have a multimodal distribution, you can have a uniform distribution, and we kind of learn all this in IntroStats, right? But then when it comes to regression modeling, GLM, linear regression, and GAM, they only focus on the mean value of a distribution. And to motivate this whole thing further, I'd like to put up a quote by Sir Francis Galton, who kind of came to this understanding already roughly, maybe 150 years ago. It's difficult to understand why statisticians commonly limit their inquiries to averages and do not revel in more comprehensive views. They so seem as dull to the charm of variety as that of the native of one of our flat English counties, whose retrospect of Switzerland was that if its mountains could be thrown at its lakes, tuned will be got rid of at once. I really like this quote. It's really good. And then here's another one from one of my PhD supervisors, which is sort of like a bit more on the point. Most empirical modeling is firmly located in the lowlands of the conditional expectation of the distribution of the response, e.g. in generalized linear models. I'm not exactly sure what he means by lowlands or what a lowland could mean, but yeah, I think it's pretty clear what the point of this quote is. So, as I just said, linear models, GLM, GAM, which probably make up most of our, applied statistics, are centered around finding the mean of a distribution. But we have all these other things that the distribution could be. So what about all these other properties? And to give you an example of what we miss if we don't look at the mean of this, if we only look at the mean of distribution, I'd like to point to a paper that was recently written by two people here in the audience, by Julian and Christy. And Julian and Christy work for the Clinical Trial Center, so that's a lot of data they're seeing. And this is a distribution that's from their most recent. This is a distribution that's most recently from their most recent publication. And this is a kernel density estimate of a biomarker for coronary heart disease. And what was sort of the point of this sort of study was to figure out whether this drug, pravastatin, is changing the distribution of this biomarker. And yeah, there's a control group and a treatment group as often. And then they basically created 4 scenarios, 4 different models. They first created models for a reduced model where we only look at the mean. That's the first and second model. One's for a normal distribution, one's for a Box-Cox-T distribution, and then the extended models that look beyond the mean. And if you guys look at this this distribution, I mean, most of you can figure out that this is probably not normally distributed, but what people would do anyway is for the normal distribution. So let's look at what comes out of this. And so this is only the first and second models, only the 2 reduced ones. And in this case, we can see that in the normal example, we would say that we can't really see a treatment effect. But using the sort of more adequate Box-Cox-T distribution, we can see that we have a significant mean shift. So I guess the first sort of lesson from this is that if we don't take the proper distribution, we might miss something. But that's not it. If we go beyond and look at the 3rd and 4th models, which are looking at more than just the mean, we can actually see that in these extended models that we see a treatment effect also on the scale term of this distribution, which is pretty cool because if we think about what a treatment effect is, it doesn't necessarily have to mean that we have a mean shift. It can also mean that we have just a general shift in distribution, not just a location. And I think in this paper, which I'll link in this distribution, in this presentation, so you guys can have a look at it later, there's another example where in both the mean effect of a normal distribution and a non-normal distribution, we don't find any treatment effect, but then we see a treatment effect in the scale parameter. So I guess the 2 lessons from this are that there's a treatment effect on the scale parameter, and this can turn a unsuccessful study into a successful study. We just haven't looked at everything properly. And if you think about how much money goes into these clinical trials, that's pretty good. So let's talk about distribution regression now that I've motivated it for a couple of minutes. In distribution regression, we assume a parameter alpha 1 to alpha k for a distribution D. And with distribution regression, we can model each of these parameters that the distribution has. So not just the mean. You can have it be modeled with a different set of predictors. So in our case, we could have an intercept term for the mean, but we could have a connection to another explanatory variable for the scale parameter, and then another one for the kurtosis parameter, and so on. These predictors can take different forms. So everything that we know from generalized additive models, nonlinear spatial random effects can be part of modeling each specific parameter. And then these parameters are connected to the predictors using what we use in GLM, the link functions are called the supportive parameter. Yeah. In the end, this allows for extremely flexible model equations. We have specific parameters that are connected to different explanatory variables in different ways. And this is pretty cool. Here's another example of when this would make sense. This is a map of Austria, which is where I'm from. And in this case, one of the people I used to work with, Nikolaus Umlauf, he created a map where he was basically interested in precipitation around Austria. And there's a few parts of Austria outlined, Carinthia, Vorarlberg, and Salzburg. I don't know why he omitted Vienna, maybe he doesn't like it. I don't know, many people come outside the capital that don't like Vienna. Anyway, so he was interested to figure out what the sort of like mean precipitation looked like. And you can see on the left graph with longitude and latitude that you know, mean precipitation is very different all around Austria. You can see sort of the mountainous regions that have sort of less precipitation, and then everything that's around the mountainous regions that's kind of more. I guess that's the idea. And but what is also interesting is that this effect is completely flipped if we look at the sort of spatial variance effect. And spatial variance in precipitation would just mean that we can't predict as well how much it rains, meaning just the variance of rain is more. And that's interesting because around mountainous regions, we seem to have less. We seem to be more sure about how much it rains, and sort of on outside the regions we seem to be less sure. It seems to be more variety. So you miss a lot if you just look at the mean effect. And that brings me to how to implement this in practice. There are many different implementations of distributional regression because it encompasses so many different things. But I would say the most prominent and most used R package is called GAML-SS, which stands for Generalized Additive Models for Location, Scale, and Shape. There is also BAMLs, which is the Bayesian version of it. In my opinion, the Bayesian version of this distribution regression has a few properties that I really like, that are really nice. I think especially the uncertainty of parameters is a bit better implemented in BAMLs. But you know, people have different opinions about this. And then there's VGAM, and VGAM is developed by Thomas Yee in New Zealand. Yeah, it's not exactly the same thing. I've personally never used it, but there is a big community of people who use it. So if you want to, you can. Yeah, so let's get started. You know, we're up and coming researcher. We're interested in figuring out what drives a distribution. Here's a distribution I took from a book written by the person who developed GAMLs. This is a TF distribution, so basically a T distribution, T family. And in this case, you know, we have Turkish stock exchange returns. And then the question is, how can we figure out what distribution is good for these stock returns? And there is one thing that I really like about GAMLs, which is this fit-this function. And fit-this basically fits different distributions to your data and prints out the deviance of that. And then you can basically select from your own terms which one has the lowest deviance, which is the best fit, and use that for your analysis. In this case, we can see that this TF distribution or just the T distribution has smallest deviance, and so that would make sense to use for our data. And of course, your distribution can change a lot depending on your explanatory variables. And in this case, you can also fit conditional distributions, which is really, really handy. There's basically three different distribution types to choose from. There's the continuous distributions, which are not bound by the negative and positive space. And then there's discrete distributions, like the Poisson distribution, which is like here. And we have mixed distributions, which I really like because they sort of they're a bit niche, but I really like them because you can basically have point parameters, and you can have sort of density estimates, which is pretty cool and exciting. Yeah, and then once you are ready to fit your model, the sort of R code would look pretty similar to R code you know from linear models and generalized linear models. You basically have a dependent variable, which is on the left side. In this case, this would be L-BOR F1. This is just a generic, basically, data set. And then you have the explanatory variables on the right side of the equation. I don't know if people can see that, but there's a little wiggle here, which basically separates the model equation. And then you specify the data set you're using and the family, which is your distribution. And then if you're ready to fit your variance parameter or your shape parameter or so on, you basically go into this argument, which is called sigma.formula. That would fit the sort of second parameter, the scale parameter. And then you can basically use the same model equation like you did in the first place for the mean parameter and basically fit this. In this case, I've fitted the sigma parameter to this random explanatory variable called LBO open. And if you then look at the summary, you get specific model summaries for both mu and for sigma, which is really exciting because you basically can interpret these parameters independently. And yeah, you can basically see what your estimates would look like for both parameters. In this case, we have an estimate for mu and for sigma, and it has p-values and everything that researchers know. And then there's tools that have been written to sort of do post-model analysis. One of these tools is by me, which was part of my PhD topic, which can be used to sort of analyze a model once it's been fit. And I'd like to quickly go through how that works. And this is my R session. Let me make it a bit bigger. Okay, so this is my my R console, and in this R console we can see that I'm trying to fit this model. In this case, I'm trying to fit a model that is about a wage distribution. It's a really old data set about wages in the northeast of the United States. And in this case, I'm trying to sort of estimate if there is a difference between the variance of different education and sort of age groups. And so this time I used the BAMLs package, and I basically fit it like this. Oops. So I'm basically loading all these models, and then I'm running the model, just as you would if you're analyzing your data set. And then this is an R package that I developed. You can basically start sort of an interface by yourself. And the way to do this is you go on the very top row here. I have to put this side a bit. So you go to add-ins, and then there's this package called DistrictVis, and that's basically a distribution regression model visualizer. And you just click on it, and then it opens up a web page, and you can select the model. In this case, I have given it the name B, which is obviously not very inventive, but yeah. And then you can see what family I used. I used the log normal distribution. You can look at the link functions that I used to make this model, and the model equations. And then you can go to scenarios and basically select different wage scenarios. In this case, I'm interested in the difference of education. These values are all just basically mean values from this data set. And I'm just creating this scenario for a high school graduate. And now I see the wage distribution for a high school graduate. And then I just select a different one, which is, that's above the high school graduate maybe. And then we have someone who went to college. And then we have someone who graduated from college. And then we have someone with an advanced degree. And you can easily just compare different scenarios that you're interested in and sort of see the predicted distribution from this. And this is all done using ggplot, so you can basically save that plot from there and use it for your publication. Yeah, if you're interested in sort of the influence of one variable, I also have marginal influences, which you can look at with properties. Yeah, there seems to be an error here. I don't know why. but normally you can look at the marginal influence from a variable on. Oh, wait. Maybe I'll go and have this one. Okay, it doesn't work at the moment. I don't know why. But yeah, you can have sort of the marginal influence of a variable. Like for example, you can see how the age has an influence on the wage distribution. Yeah, cool. And with that, I go back to my presentation. Yeah, and with that, I'm basically done with this introduction. Yeah, thank you all for coming. Cool. Two things. The QR code that is here is a QR code to my slides. So if you're interested in figuring out how this all works, or you want to have a reference, please just scan that QR code. But in any case, I'd love to open up the audience participation and figure out if anyone has any questions. Yeah, David.
So if this generalized modeling, is there a better way for you to work out what the predicted value would be? Like say if X was time, and you would say, okay, based on this, we predict that the gym example at 6:34 p.m. these would be the predicted values of that. Is that functions in your tool, or is that a function that you have to get elsewhere?
No, you can do that with the tool that I developed. You can either get a graph that outlines the influence for the whole range of the variables, so time, or you can select a specific time and then see what the predicted distribution would look like for that time. Yeah, both is possible. And yeah, that definitely is part of it. Yeah.
And that would be in the table.
Yeah, that would be in the right section. Yeah, that I for some reason can't show up today. Yeah.
Is these that tool is that specific for these GAMs, or is it more universal to be used for other types of modeling?
No, this is only for distributional regression models. Okay. So this can only work with either the GAMOS package or the BAMOS package. Yeah. But it can't work with, I don't think it can work with GAM at the moment. Yeah. Yeah.
Question in the chat. Understand the connection with Weibull distribution. Can you elaborate more?
Yeah. Oh, thanks, Ali. Okay, so the question is, or the statement is that someone didn't understand the connection to the Weibull distribution. So let me bring up that slide again. Yeah. So this is a graph where we see the different density functions of a Weibull distribution depending on different parameters. And the legend is maybe a bit small, but basically we sort of vary the parameters of the Weibull distribution in sort of the first and last case. We have, for example, we have 0.5 and 5. And I'm pretty sure this means that we have a location shift. I mean, I'm not 100% sure, maybe Jillian knows this more, but I'm pretty sure the first parameter of the Weibull distribution is a location shift. So if you were to connect this to explanatory variables, you could model a location shift difference with the first parameter. And then the second parameter is here. Second parameter is always the same one. It's always 1. So in this case, it doesn't model a scale shift. Not sure exactly what the second parameter does, but you can use other parameters to model the location, the scale shift. Yeah, you can basically use different parameters to sort of like change the shape of the distribution and the location. I hope that answered the question.
Another question in the chat.
Yep.
How do you control for type 1 errors? data dredging when you are potentially looking at so many options for the distribution and differences in parameters.
Okay. Can you say it again?
So how do you control for type 1 errors / data dredging when you are potentially looking at so many options for the distribution and differences in parameters?
It's a great question.
We probably pre-specify the video is best.
Yeah, the question was why or what can you do to change, or what can you do to control the type 1 error and prevent data dredging, which I have never heard of. And you know, given all the different all the different possibilities of distribution. Christy, what did you say?
I was saying that you would specify that you go with the one with the best fit in terms of AIC or whatever, but we were just saying this wouldn't be a primary analysis.
No, but the question about type 1 error is still valid. Yeah, that's not a primary analysis. I think the answer is you don't. There is extra type 1 error there implicit in that selection process that you're selecting along to select distribution, and then the parameters for the predictors for all of the model parameters to count for. Yeah, so the type 1 error is very.
Is it about, you know, how well you specify your analysis protocol? What do you put in the protocol?
As a bit that people choose, but as you say, take the lowest AIC.
I think, yeah.
But that's all.
Unless unless
think-
you specify the actual distribution, it's going to be error.
Yeah.
Distribution.
I think, yeah, it's good to reiterate that this shouldn't be like a complete data-driven process. Like, I don't think you should throw any possibility of model specification at data and just take the lowest AIC. I think what should be done is, ideally, you have some kind of theoretical derivation for what you're trying to fit, meaning you kind of know that your distribution is bound to the zero, or you know that your distribution cannot be above 100 or something. And then you go from there. You think, oh, could my explanatory variable have a linear or a nonlinear influence on y? But I think, yeah, that's a good point. I think not going completely data-driven and trying everything out, but trying to come from a theoretical derivation to this is the best idea. Would you guys agree with that?
You're not eliminating the problem.
Yeah, it's more about minimizing than eliminating. Yeah.
Like any analysis that's basically your exploratory data analysis, plot the data, decide what distribution.
Yeah, any analysis, even with distributional regression, doesn't, you know, prevent an exploratory data analysis part of this. Chris?
Well, I guess often when people talk about that, they worry about p-hat. It doesn't really apply to here to some extent. So you have to pick a distribution, mix up. So you're just going with one data suggesting best.
And the reviews.
Yeah, exactly. Yeah. But it's not like, it's not like it's testing lots of different things for pulling up p-value.
Yeah.
It's this list. You
Exactly.
have to go with something.
Yeah, but it's funny because the normal distribution is always the go-to distribution for stuff, but always the go-to distribution for any sort of thing seen in the wild. But if you look at the graph of this biomarker, for example, even though people you know, would probably use even normal distribution to analyze this, it's pretty clear that you should, like, it's bound by the negative scale.
Complexity in Mr. Pro as well is that it's
Mr. Pro.
Yeah, Mr. Pro, that's what I call it. From first name basis. That it also has sensory issue as well that is glazed over.
Yeah, that's why it's censored, right?
Yeah.
Yeah.
There's a detection limit, yeah, on the lower end. So there's additional complexity.
But that was the it was a sense of distribution.
Yeah. The last,
That's where that curve sort of cuts right off.
That's right. Yeah, it's like 0.00 something.
I was sort of looking at it as zero, but it's not zero.
It's just about,
Yeah. the last thing I want to say about this is, if you in the room or in the audience have something that you're interested in analyzing, come and request a consult with the SIH stats team, and we can help you work through whatever you're trying to do with distributional regression. Any more questions? I don't know who was first. Alex?
You're an applied statistician. Just wondering. But I was just wondering, like, about the applications. So, you know, rainfall, variance, you know, the mean being acceptable is really cool. But just wondering if you see an application where, like, you have predictors that really affect the location, but the scale is affected by a completely different set of predictors. You come across anything like that?
Yeah. So the question for the Zoom audience was, someone stated that I have become an applied statistician, and is wondering about how often I come across a situation where the explanatory variables have a different influence on mean and variance. And to be honest, often they don't, but often they also have an influence on the variance, which we don't take into account. And especially if you look at the assumption of a sort of like a constant dispersion term in linear models, generalized additive models, and generalized linear models, that is almost never the case. Like, you almost never have a situation where your error distribution is neatly around the line. So almost in any analysis that you do, I think you should check for whether your scale parameter, even if you are super sure that your data is normally distributed, to check whether the variance of a normal distribution is also dependent on your explanatory variables is so important, because, you know, if you think about heteroscedasticity, where the observations stray further from the line, the bigger x gets, or smaller x gets, that can be perfectly encompassed by a scale term that's connected to x. And if you don't do that, you know, your mean influences will still be valid, but you'll miss a whole lot about, you know, the sort of like interesting influences that you're trying to show in your research. And if you think about a multi-year research study, just, you know, checking for this and using models that can take scale changes into account is just makes sense, I think. David?
I don't know if this is the right terminology, but how many training examples do you need to create these types of models?
Yeah, this is a great question. The question was, how many training examples? You mean how much data?
Yeah, I mean, you know,
Yeah.
that word, just data points.
Yeah, how many data points do you require to fit this analysis? I mean, this is a really good question. One thing I will say is that a distributional regression model has more parameters, because if you connect more parameters to explanatory variables, you even in a parametric sense, if you don't do any smooth functions, even in the very simple case, like let's say you have the income that's dependent, where the mean shift is dependent on age, but also the scale shift is dependent on age, you have twice as many parameters as before. And with twice as many parameters, I think you need twice as many data. Chris, my boss Chris, he had a rule once that I really liked, something about 10 observations per parameter or something. Is that what you said? Yeah.
Statistical rules tell me 10 better per estimate than maybe.
Yeah. So yeah. So that's something I would start with. Yeah. But it would be interesting to do a sample size calculation for a distributional regression model. I've never done that before. Yeah. Any other questions? Yeah. Any other questions? Cool. Well, thanks everyone for coming, and online for being there and asking great questions, especially the person with the type 1 error question. That was really good. And I hope to see some of you at our consults or trainings. And yeah, have a great day.